Yeah, having understood various uh, low carbon steels, medium carbon steels and high carbon steels, now let us try to understand various uh, other types of steels. Okay, for example, alloyed steels, okay, high alloyed steels such as stainless steels and so on. So the first one very popular classification of steels in alloyed steels category is your stainless steels. Okay, we all know that stainless steel predominantly consists of in other words, the main alloying constituent for the stainless steel is chromium, okay, which will be having at least 11%. Okay, we have your iron carbon, along with that you have minimum 11% of chromium in case of stainless steels. Of course, that is the main reason for its corrosion resistance, but you can also achieve this corrosion resistance by using either nickel or molybdenum also. Okay, so if you see the stainless steels, they can be broadly divided into three categories. Those are martensitic, ferritic and austenitic stainless steels. Okay, what are they? If you see the martenitic stainless steels, they are heat treatable. Okay, for example, these steels you can, just like your high carbon steels or medium carbon steels, you can bring it to austenitic temperature and quench it so that you get martensite. Okay, we call them martensitic steels. Okay, whereas ferritic stainless steels, what happens if you see the phase diagram of ferritic stainless steels, you will be having more of ferrite. Okay, your austenite region, whatever you see in the normal iron carbon phase diagram, that will be very small in size. Okay, that means you have, even at elevated temperatures, instead of austenite you will be having more of ferrite. That means you cannot heat treat it, right? You cannot get martensite. Why? Because even if you go to the high temperatures, if you want martensite, you need austenite, right? To get austenite, you have to go to high temperature normally. But in this particular case, since you don't have austenite, you have only ferrite, you will not be able to get martensite. Okay, that is a bad part, but still they are stainless steels of ferritic type. They have their own advantage. They are corrosion resistant. Only problem is you cannot heat treat and improve the strength further. Okay, so the similar is the case with another type of steels. Those are austenitic stainless steels. Okay, this is the third variety of stainless steels. In here also you cannot heat treat it again. What is the problem? You have austenite stable even at the low temperatures, even at room temperatures. So now what happens? It will not be forming austenite, martensite. So you need not heat it actually. Okay, even if you heat it and cool it, you will not get martensite. Okay, because austenite is already stable even at room temperature. Okay, so that way your austenitic stainless steels and ferritic stainless steels are non-heat treatable, whereas your martensitic stainless steels are heat treatable. Okay, now if somebody asks can you heat treat austenitic stainless steel, you should tell no, and you should also give the reasons. Okay, now both martensitic and ferritic stainless steels are magnetic. Okay, that is one important difference. Okay, so here I asked the question why ferritic and austenitic stainless steels are not heat treatable. Anyway, I have answered that even before asking. Okay, right. So these are the examples of different stainless steels. Of course, it is important for you to know what happens if you add different alloying elements. Okay, for example, if you add carbon, what happens? Anyway, in iron carbon, steels, you have carbon. Even if you keep adding carbon, what happens? You improve the hardenability. That means it is easy to get martensite if you increase the carbon percentage. Why? Because your C curves will move to the right. Okay. Similarly, the strength, hardness and wear resistance also increases with carbon addition. Similarly, chromium, if you add chromium, you can improve all this toughness, hardenability and so on, and also it improves the corrosion resistance more importantly. And again, similarly, cobalt and other elements, you can see what are the effects of each of this alloying element addition, okay, on the steel. Okay. Similarly, if you want to talk about the other alloying steels, okay, or alloy steels, apart from steels, you have tool and die steels. Okay, typically tool and die steels are high carbon steels. You know that, and they must be having high impact toughness, wear resistance at room and elevated temperatures. That is the main difference, okay, even at high temperatures, because if you take the die, usually we use dies, okay, to pour some or to use some material at high temperature and give it a particular shape. So that means your dies should possess strength even at high temperatures. It should not lose its strength at high temperatures. In such cases you will use this tool and die steels, okay, with high carbon and other things. So you similarly have different another variety called high speed steels, okay. The main importance in high speed steels is to maintain the high hardness and strength even at elevated operating temperatures, okay. And you use these high speed steels especially for the machine cutting tools, okay. They are of two types, M type and T type, based on whether it is molybdenum type or tungsten type, which one is predominant alloying element and so on. Similarly, you have die steels specifically where you have toughness, high resistance to the wear and so on, okay. So if you see here, these are the different summary of different tool and die steels. You have high speed steels where they are M type or T type based on molybdenum or tungsten type. Similarly, you have whether you hot worked or cold work, you have different symbols for that. Similarly, mold steels, special purpose steels, water hardening steels, all these are different classification of your tool and die steels, okay. And of course, if you see the applications for selected carbon and alloy steels, you see for aircraft, okay, forgings and tubings, you have different steels, and for gears, car and truck gears or landing gear, and so landing gear of the aircraft, you have different steel, okay. Automobile bodies, you have different steel, bolts, camshaft, chains, for all these steels you have different steel. What are these numbers? These are the designations, okay. To see the exact chemical composition, you can always see the data book for a particular designated steel, what is the chemical composition, okay. Right. If you see the next part after steels, you have the cast irons, right. And in case of cast irons, the very first important concept you have to know is, we know that in iron carbon diagram we have cementite, right. So if you have very high percentage of this cementite, okay, and if you take any for example cast iron typically, okay, you can actually that cementite is very hard in nature and it is also a compound, okay, it is not a solid solution, right. I have already mentioned this. So this cementite, as I said, is undesirable in some aspects simply because it is brittle in nature, highly hard, okay, hard material. Why? Because it is a carbide, right, it is a compound. So can we have this in some other form? In fact, you can have this cementite decomposed into ferrite and graphite, okay. That is the equation I have shown here. You can induce this kind of reaction in case of cast irons with high percentage of cementite, which is very fruitful to reduce the brittleness and so on, provided how this happens, simply it will not happen if you go at very slow cooling rates, okay. Typically you can get graphite, and also you can promote this reaction by actually having silicon in the steels, typically more than 1%. So that means if you have more than 1% silicon and if you are cooling the material very slowly, your microstructure, if you see, you will be having ferrite and you will be having graphite, okay. Yeah, that is what it is mentioned as slow cooling, okay. Now let us see various types of cast irons, okay. So you see, if you go very slowly, you can have below this, okay, 740 degrees Celsius, you can have ferrite plus graphite, okay. If you have silicon more than 1% and slow cooling, this is the combination, okay. Now let us see the different types of cast irons. If you see the gray cast iron, see the name has come from, if you take this gray iron, if you fracture it, the fractured surface looks in the gray color, okay, and that is why it is called gray iron. And now why it looks gray? Because in gray cast iron, your graphite, whatever graphite you have, it is in the form of flakes. Okay, its morphology is in the form of flakes. You see, very acicular nature of graphite. It's not equiaxed, or it is not spherical or something like that. So it is having graphite in the flakes, and unfortunately these flakes have, you know, sharp tips, and they you know, act as the stress concentration you know, regions. So that means it will fracture in brittle, you know, it will give brittle fracture, and the material will be brittle in nature, so which is not, you know, recommended, okay, for many of the engineering applications. So the challenge is to change this morphology of this graphite flakes, okay, this flaky morphology, okay, that is there in the gray cast iron, that you can achieve, okay, if you add some magnesium, okay, or Ce, okay, Mg or Ce, if you add, what happens, this graphite in flakes graphite will be converted to spherical, or, you know, nodules, okay, into the nodule form, okay, spherical form. So now you removed all the sharp edges, you got nice beautiful spheres of your graphite. So now which will improve the machinability of the cast iron, okay, it will improve the ductility, and it is always good, right? So that is the main difference between these two, and ductility can be close to that of steels. You know, steels have good ductility because of low carbon, and if you have if you add this magnesium, or, you know, this Ce, cerium, what happens, your graphite flakes will change the morphology to spheres, spherical or nodules of, you know, graphite, thereby improving the ductility to close to the steels, okay. If you see the white cast iron, you know, typically you will be having, if you don't have graphite, what you will have? You will be having cementite, right? Fe3C, okay, that is carbon existing in the form of cementite, okay, as a compound with the iron carbide. So if you have iron carbide as such, okay, as cementite, then you see the microstructure like this, and if you break it, okay, the fracture surface looks like white. So that is why it is called white iron, okay, and it is not desirable, right, because it is hard and brittle. So typically you don't want this white iron, only in very few applications, like where you want very high hardness, for example ball bearings and all, you will be using white iron for those applications. So if you there is another, so since you don't want cementite to be in this form, you know, you don't want cementite, so what you do, you can heat treat at 800 to 900 degrees Celsius. What I mean to say is, you take the white iron and heat treat at higher temperatures for prolonged time, and what you get, all this cementite again gets back to your graphite state, okay. You see these dark, you know, rosettes we call, or clusters of this graphite will form, okay, and this becomes again malleable or ductile in nature, okay, because of change in the, because it is no more a hard brittle cementite or carbide phase, it is now in fact ferrite and graphite, okay. In fact the microstructure looks like very similar to your ductile iron or nodular iron, except for it is not spherical, rather it is only cluster of graphite or rosettes, okay, of graphite, okay. Yeah, now these are some of the important points about each of one that I have just discussed. So flaky graphite, in case of grey cast iron, machinability is excellent. Similarly, it is used for engine cylinder blocks, okay, liners, brake drums, clutch plates, and machine beds, especially because it has got very good damping properties. So for machine beds we use grey cast iron, okay. Similarly, ductile iron, if you add magnesium, you can have spherical, you know, graphite instead of flaky graphite, okay. So these are the applications. So these are all we have discussed just now. So if we move on to the non-ferrous alloys, let us discuss in the next module about some of the important non-ferrous alloys, okay.